internet connection. Kong, you maybe ought to do all of this because I keep losing contact.
Yep. Okay. I can try. Let me try to look at the CV of the speakers.
Well, I can do it for the no. I can. Well,
maybe you want to try to turn off.
Okay.
You want to try to turn off your video.
Connection.
Turn off your video and then I speak. Try to speak.
It doesn't seem to matter so much. Huh?
No, I think it's better.
Is it? Well, temporarily, yeah.
Yeah, it certainly improved.
Yeah, it does.
Okay, I can try to do the ends. Okay. Yep.
Maybe Bob, like, should I start give the introduction?
Yep.
Okay, let me try to share my screen. Okay, cool. All right, good morning, good afternoon, good evening, everyone, depending on where you are. So I'm Kong, and then welcome to our, I lost track, maybe like 7th or 8th of our Zoomina session. So first of all, I would like to give you a brief introduction to our series. I mean, if this is your first time here, so if you want to be updated about the future Zoomina series and who are the speakers, please subscribe to our mailing list. I will actually copy this link and put it in the chat room so that you can subscribe it, so that you will be notified if there's any changes, if there's any update on our future series. And also, if you want to look at our previous speakers, all the talks that were previously recorded were posted on our website, so which is here. And so this is how our group website looks like, and then it has all the speakers, and you can access the video. And then on top of that, if this is your first time here, feel free to ask questions and use the Q&A function that you can see at the bottom of your Zoom interface. If you are not very familiar with the with the Q&A function, feel free to raise your hand. I will still allow you to speak, and then you can ask the question verbally. But in any case, do not type your question in the chat, because most likely I will not be able to read it. And also, you can type your questions like anytime throughout the presentation, and you can also, if you feel like some of the questions that you would like to comment on it, you can answer or comment, and you can also upvote your questions. And the questions with the highest number of votes will get asked first. And one last, I should introduce this before. I mean, I've received some emails about question about would the Q&A or the questions in the past session be posted online so that you can look, we can look at it. Yes, actually I did this like long time ago, and all the Q&A sessions, all the questions were actually like put in the Dropbox that I actually had, where the link is actually like included on our group website. So I'm just look at it. So these are all our past sessions. So for example, last week when we had Aaron and Evans. So sorry, just go back. These are all the questions, and you can look at it, and also the answers are here if they are typed in. If you feel like commenting on it, or if the speakers of the past session would like to answer some of the questions, you can always type here. You just have to log into Dropbox. You can type in your answer, and then maybe if you want to direct the question to some of your friends, if you know their email, for example, if I say, okay, I want to know to hear Bob's opinion, and then I just click add, and then I have Bob's email, and then I just do this, and then Bob's email will get he will receive an email from Dropbox and get notified that, hey, Kong has a question and he wants to direct this question to you. So feel free to comment or do anything that you like. So so that's all from my side, and now I would like to pass the session to Bob so that he can introduce our speakers today. Bob.
Thank you, Kong. Thank you. I have a somewhat unstable internet connection today, so I'm going to keep my video off, hoping it will improve the situation. Today we have two excellent speakers, one from UCSB, Sheetal Jain, who's a postdoc in Sanghi Han's group, and an IIya Kuprov, who is a professor at the University of Southampton. And Sheetal is our first speaker, and he's going to be telling us about DNP in p-doped zeolite. So Sheetal, you want to take the virtual platform, stage, whatever, and tell us about your research.
Yeah, thank you, Bob. So let me share the screen.
And be sure and speak up so everybody can hear you.
Yeah. So this is fine, right? You can hear me.
Yeah.
Okay. Okay. Yeah, so thank you, Bob and Kong, for organizing this webinar series and giving me an opportunity to present my work here. I'll talk about using DNP Enhanced NMR to characterize these phosphorus-modified zeolite catalysts. And we found some new sites that I would like to discuss with you today. This is a highly collaborative project with the Catalysis Center of Energy Innovation, which is locally supervised by my supervisor, Professor Songyi Han, as well as Professor Susanna Scott at UCSB. The samples were provided by the groups of Professor Michael Sapastis at Johns Hopkins University and Wei Fan from UMass. And Stavros is involved in the DFT calculations as well as all the ongoing discussions. Ternuma is involved in the project right from the sample handling to data interpretation and all the discussions. I would also like to thank my colleagues at Han Group in Han Lab for their wonderful support, and the funding is coming from DOE. So a brief introduction to the materials. These beam modified zeolites are heterogeneous catalysts, and these heterogeneous catalysts are critical in biomass conversion reaction. So for example, here in this, one of the steps is to convert DMF into paraxylene. And there have been several heterogeneous catalysts that are being used for this reaction, and some of those are compared here. So the black bars here are the conversion efficiencies, and which is quite high for many of those, including phosphoric acid and other zeolites. But when it comes to the selectivity towards one of the products like paraxylene, then we see that these phosphorus modified zeolites P beta and PSPP, and I'll talk about those in the next slide, they have exceptionally well performance, giving up to 97% of selectivity. Now the question is why that is the case, even though phosphoric acid itself is a catalytically active for this reaction, why the selectivity increases by putting the phosphoric acidic sites in the zeolites. And that's something we will try to understand today. Now, briefly into the zeolites. The two types of zeolites are shown here. The beta, which is a conventional zeolite, and then the other one is PSPP, which is recent, relatively recent in 2012. The group of Sapastis, Professor Sapastis published it, and this has this interesting structure. Now, the phosphorus sites can be located inside the pores of these zeolites, and this is just a scheme. By no means this is a structure, real structure. But the point here is that these phosphorus sites can form direct SiOP linkages with the zeolite framework, or they can be confined in the pores without forming any covalent bond, or they can be in oligomeric forms. So all those different possibilities are there, and they all have different acidity maybe, or different roles in the catalytic activity. So knowing the distribution is the first step towards probing the catalytic active sites. So for that, we had these questions to answer, as I said in the last slide, that what type of phosphorus sites are present in these PSPP. So in this talk, I'll mainly focus on PSPP zeolites. And if you look into the literature, there have been two types of sites proposed. One, which is framework bound sites at the top row here, which the nomenclature for which is borrowed from the silicon NMR nomenclature. So basically, if you replace one of the protons in the phosphoric acid by either silicon or phosphorus, we call it Q1. And if you replace two of them, then it's Q2, and all three of them, then it's Q3. Now, all three can be replaced by silicon, and that will be a framework bound site, and they can be oligomeric sites. Now, the challenge here is that the chemical shifts of the oligomeric sites and the framework bound sites of same type, that is Q1, for example, are very similar to each other, and at least they are not easy to distinguish by solid state NMR spectral resolution that we have. And then another interesting question is that how does water affect these phosphorus sites? Because water is a byproduct in these reactions, and it has been proposed in literature again that both the POSI linkages and the POP linkages are susceptible to presence of water, and they can break and convert these sites from one type of, so for example, Q3 to another type of sites like Q2. So to answer those questions, we used NMR, and we started with the dry state of the sample. So that by dry, I mean we heated the sample overnight under vacuum condition for 12 hours, and then loaded it into MES rotor under the night condition, and recorded direct phosphorus NMR spectrum at 800 megahertz spectrometer with 20 kilowatt spinning. And this is what we get. Now, if we take the rotor out and just expose it to air for 1 minute by opening the rotor cap and closing it again, just simple experiment, and we see a dramatic change in the signal pattern. And that tells us that these samples are sensitive to the presence of water. And now one can fit them using top spin, and the thing that we notice here is that their chemical shift, the isotropic chemical shift, is minus 43 ppm, which is why we assigned it to Q3 based on the literature chemical shift values. But their anisotropy changes from 190 ppm to 160 ppm just in 1 minute of air exposure. Now, if we see those were the two possible Q3 sites based on the polyphosphate POP linkages or SiOP linkages, and we can directly here disregard one of the possibilities because it has been reported here is one example, but there are many other papers where they reported the chemical shift anisotropy is around minus 300 ppm for this kind of sites. So basically, this tells us that there are framework-bound Q3 sites being formed in the dry PSPP material. Now we can do this experiment again by opening the rotor cape, and we see that on at longer exposure time, the new sites, these Q2 and Q3 sites, start to pop up. And after long enough exposure time, we start to see the Q0 site, that is phosphoric acidic sites, start to emerge. And if we plot the intensities of these sites as a function of air exposure, and the air exposure here is basically a quantity, is representative of water content in the sample, then what we see is that the Q3 sites linearly decrease. The Q2 sites increase in the beginning and then start to decrease. And both Q1 and Q0 sites almost monotonically increase in this region. So basically this indicates that there is a sequential hydrolysis going on, and this is one of the possibilities, that in the beginning we have Q3 sites, and on exposing it to water, they convert into Q2 sites, that explaining this, the increase in the Q2 intensity, and then those convert to Q1, that's where they start to decrease again, and then Q0. So right now we are in the regime where Q1 and Q0 both are being formed, but if we give it a long enough time, most of the intensity will converge to Q0 peak intensity. However, it's not yet clear whether these are polyphosphates or framework bound. This is just one example, but it could be very well, some of the, at least some amount of it could be still some more complex polyphosphate sites. So to probe it, the SIOP and POP linkages, what we need is correlation spectroscopy. But for correlation spectroscopy, we need DNP because the sensitivity is a severe limitation here. And that's because the ratio of phosphorus to silicon in these materials is quite low. There are less than 4% of the phosphorus. And then in the dry state, at least, there are no protons, so you can't even use CP to enhance the sensitivity. And the natural abundance of silicon 29 doesn't help either. So we used TechPol and dry TCE as a non-aqueous solvent, and DNP sense, and here are the results. So both silicon and phosphorus NMR are sensitivities are significantly improved. So here the off signals are taken with 22 minutes of signal averaging, and the on signals are with 40 seconds of signal averaging. And we see that a decent signal to noise ratio is achieved, and we can use this for more advanced NMR experiments. Now, one thing here is that the MS frequency now is 7 kilohertz. That means that in phosphorus spectrum, the sidebands are crowding the total spectrum. And the Q0 and Q1 sites are now, their isotropic peaks may be hidden under the sidebands of Q2 and Q3 sites. Moreover, we would also like to see their chemical shift anisotropy individually. And to do that, we decided to use a pulse sequence known as respiration CP. And this is my PhD work. The pulse sequence is shown here. We have earlier used it for proton to nitrogen 14 or deuterium to carbon polarization transfer. Here we are using for proton to phosphorus transfer. And the idea is that you use a rotor synchronized blow with almost half a rotor period, X pulse, and then another with phase flip. And then at the end of the rotor period, you use the short pulses to tilt the Hamiltonian. So the matching condition is that during those short pulses, the RF frequencies should be almost the same. In fact, it's the tilt angle should be the same, and one can show that you can increase the pulse length if while tilt angle is same for both the short pulses. Now, having the short pulse helps it combating against the CSA and quadrupolar interaction, which are highly anisotropic. However, the feature that we are interested in this project here is the frequency selectivity. So it is known that the respiration CP is narrow banded pulse sequence on the channel where you use a short pulse only per rotor period. And here is the simulation where the simulations were run with these on Simpson using these parameters. And if we see that 0 means you are on resonance, then it's effective in plus minus 1.5 kilohertz range. So it's quite narrow banded. But if you go a rotor frequency away, that is plus 7 kilohertz or minus 7 kilohertz or 14 or so, then you see that the sequence performs equally well there as well. So this is really a nice feature, because now we can use this sequence to selectively excite, to selectively transfer the polarization to one of the phosphorus sites while retaining its chemical shift anisotropy pattern. So just to give an idea that if we overlay the CP spectrum that I showed in the previous slide, you see that you can now select these Q3 sites together with its sidebands while suppressing the Q2 sites. And that's exactly what we did here. So here is the comparison of CP with respiration CP. And you can see that in respiration CP, the Q2 sites are suppressed significantly. Now, here in respiration CP, this is also a Q3 based on the isotropic peak, and there still can be Q0. We'll talk about that later. But if it's Q3, then the possible sites are these type framework bound, because we have already said that these are probably not present in there. But when we fit them using CSA, we see that there are two isotropic sites. Both are in Q3 region. They have slightly different chemical shift anisotropy. So that made us think about some other possibilities which are probably present in the system. And therefore, these types of mixed sites, we call them, which are partially involved in both framework bound as well as polyphosphate linkages, may be the reason why we see the multiple types of Q3 sites present in this in this spectrum. And this is important because these sites are usually not considered in the, at least in the calculations when they analyze the catalytic activity of these materials. So having, showing the possibility of these type of sites is important, and that will enhance the understanding of the catalytic activity of these materials. Now, we will look into those in more detail with SIOP and POP correlations, but before going to that, we can now use the same trick to see selectively Q2, Q1, and Q0 sites. And that's exactly what we did here. Sorry for the crowded slide, but basic idea is that the Q3 sites that I showed here have two isotropic peaks. Now, when you shift your carrier frequency during respiration CP to minus 25 ppm, that's when you target only the Q2 sites, and you see Q2 selective spectrum here. And the isotropic peak is in Q2 region. And its anisotropy is now less than the Q3, which is understandable because these sites are probably more mobile. Now you target Q1 site and you see that there is a small amount of Q1 present in the sample, because this chemical shift, based on the chemical shift in Q1 region, together with an overlapping with the site from the Q3 region. Interestingly, when you target the Q0 site, when we targeted the Q0 sites by putting the carrier frequency at 0 ppm, we could not fit the spectrum using the isotropic shift at 0 ppm. Both the isotropic peaks were in the Q3 region. And this tells us that most likely there are not Q0 sites present in the dry state. The intensity at 0 ppm belongs to the Q3 site, which is at around minus 43 ppm. Okay, and we can confirm it with the different spinning frequency. The spectra became more crowded, but we did confirm it, and that is the case that there are no Q0 sites present in these samples. But now coming back to the question of the multiple sites, the new kind of sites that are possibly present in these samples. So now we have this kind of distribution of the sites. So we need a more general nomenclature, and we decided to use these two, N and M index, where N index is same as before, which is the number of protons that has been replaced by either phosphorus or silicon. So these are the Q3 sites when all three are replaced by POP in this case. But the lower index now tells you explicitly how many of those are silicon. So remaining is automatically phosphorus. So for example, if you see these Q3 sites, if all three are framework bound, then the Q3 and then the lower index is also 3. But if all three are polyphosphates, then Q3 and the lower index is 0. And the in between the mixed sites will have the N between 0, the M index between 0 and the N. Okay, one thing here that all sites of these different N will have relatively well-resolved chemical shift, isotopic chemical shifts, but the sites that are different in only the lower index, they are usually overlapping, and those are really challenging to distinguish, especially by 1D NMR. So we decided to use DCP for silicon filtered phosphorus NMR spectroscopy, and this will tell us that the sites that are closely linked to the framework should appear in these, and those are not bound to framework should not show up in the DCP spectrum. So here is a comparison of the CP, which I showed earlier, and you see that this peak is now not Q0. We are now sure that this is the sideband of Q3. And we see that in this, both the Q3 sites are present in both DCP and CP almost equally strong. But the Q2 site, the peak intensity, the relative peak intensity of Q2 sites decrease in DCP relative to CP. This is a hint towards that the Q2 sites may not be the framework linked directly. Now we can confirm it further by recording the buildup curves, and we see that the buildup of the Q3 sites for the DCP is faster compared to the buildup of the Q2 sites, which is almost in the linear regime. So that's why there is a large uncertainty. So based on these observations, what we see is that there are these framework bound Q3 sites, which are these possibilities, are highly likely. But then there are some sites, for example, framework bound Q2 sites, which are less likely. Some of the sites, for example, this one shown here, a Q3 site linked to two of the Q2 sites, is also less likely because that would mean higher Q2 intensity than Q3, especially under CP conditions, but we see the opposite. Similarly, purely framework bound Q2 sites are highly unlikely because their buildup should have been faster. So we start to get some idea narrowing down that what type of sites may be present in these samples. But now the next question is, before going to POP, is also to see how these sites behave in presence of water. So for that, we prepared samples with partially hydrolyzed material as well. So here you see the near dry sample, which I was showing so far. And if you compare it to the partially hydrolyzed sample with some amount of water in it, then you see that the Q3 sites decreased, Q2 increased relatively, and Q1 is now significantly present there, and there is maybe tiny amount of Q0 sites present. And in the almost fully hydrolyzed sample, most of them are Q0 as expected. So all are the DNP experiments using the same scheme as I showed earlier. So in the remaining talk, we'll focus on these two. We already discussed the SIOP, the silicon phosphorus correlation in this state. Now let's see silicon phosphorus correlation in the partially dry state. So here is the same comparison of CP and DCP. And what we see here is that the Q1 peak, which is almost equally intense in CP to Q2 peak, is almost disappeared in the DCP part, telling us that the Q1 sites are most likely not framework bound in this state of the material. We also see that the buildup curve of Q2 now becomes faster, and it gets close to the buildup time of the Q3 site in the dry state. That tells us that now in this state, there are more likely some framework bound Q2 sites are present. So in this state of the matter, we see that these framework bound Q1 sites linked to another Q2 sites, framework bound Q2 sites, sorry, and then purely framework bound Q2 sites are possible. If we look into the Q1 sites, which are certainly present here, but they are most likely in the polyphosphate form. So they are in the POP linkages rather than in POSI linkages based on these results. So now we can, based on so far these hydrolysis results, we now start to see two possible schemes. That there can be purely framework bound Q3 sites in the dry state, which hydrolyzes to Q2 framework bound, explaining the fast buildup of Q2 in the partially hydrolyzed state, and which can be further hydrolyzed, forming Q1 and then ultimately to Q0. However, we haven't seen any evidences of these type of sites, but we cannot ignore it totally. This is certainly one of the possibilities. Another possibility, which is more interesting, is that there can be mixed sites present in the dry state. This Q3, Q2 sites that are linked by POP, while the Q3 sites are linked to framework. And now these hydrolyzed, and then we see that new Q2 sites, which are now directly linked to framework, are emerging, which explains why DCP of the Q2 became faster in the partially hydrolyzed state. And then this will hydrolyze further to form polyphosphate chains and finally to 2,0 sites. Now to confirm these POP linkages, now we can do phosphorus-phosphorus correlation spectroscopy. So that's what we did, and we used RFDR for it and kept the mixing time to 714 microseconds, that is 5 rotor period. And I did the simulation, and if there is POP linkages present, then correspondingly the polarization transfer should reach at its maximum by this time. So we see here are the correlation spectra, and we see that these Q2, Q3 correlation peaks are emerging, quite intense peaks, clearly present for both side bands as well as the isotropic peaks. So this tells us that these type of linkages are present in the dry samples, confirming these type of sites are most likely present. Now these sites we cannot disregard based on these results because these are also Q3, Q2, but we can certainly see that the possibility of these are low because the number of Q2 sites are not higher than Q3 sites in this sample based on the intensities that we see. Now we can see the partially hydrolyzed sample again and compare the RFDR spectrum of the two. And we see that in the partially hydrolyzed case, these new Q1, Q2 correlations start to appear, explaining the appearance of these type of sites where Q1, Q2 and, this type of sites where Q2 and Q1 sites are linked by a POP linkages. So this, based on all the summary that the respiration CP, DCP, and these RFDR spectrum, now we see that these type of sites which were present in the dry state and their evolution to polyphosphates and finally to monomeric phosphoric acid is one of the possible sites that explain all the NMR results. So basically based on these results, we have seen that DNP Enhanced NMR can provide detailed information about the possible phosphorus site distribution in these materials, which is crucial to understand their catalytical activities. We have seen specifically these sites highlighted in this triangle here, which were not proposed before, but those are certainly possible. And we use these techniques to probe these sites. With that, thank you, and I would like to take questions.
Okay, thank you very much, Sheetal, for your. I think it's a very rigorous work where you try very many different techniques to try to reach the conclusion and saying that, oh, this is like it all seemed to like in very good agreement with each other. So like maybe I will just start with a question first, so that the attendees like you have like time to type your question also and vote it. So I'm just curious. So so for the DNP enhancement, how much did you get?
The enhancement number. So
TechPol and TCE, right?
TechPol and TCE, that's what we used, and 16 millimolar TechPol in dry TCE, that's what we used. I didn't calculate the enhancement number because it varies, but you can see it was in the order of like 80 to 100 somewhere. Because
they will also change depending on how much you open the rotor and how much water
that
right?
is certainly a possibility because TCE is can evaporate, can go out. So, but what we see luckily here is that even in the partially hydrolyzed state, the DNP is working. We have seen the enhancement in both the states.
But the enhancement number would change depending on the air time. Is it correct?
That I cannot disregard that possibility. I haven't seen much variation, but I won't be surprised if that is the case. However, the point here was to see the individual sites, not.
Yeah. So. Okay, cool. So like I will look at a Q&A. So the first one is, would it not make sense to separate phosphorus isotropic shift from CSA with something like PSSS? So
I wanted to get here both of them simultaneously. The phosphorus isotropic peak individually, and then the entire sideband pattern. Maybe this is one of the techniques that can also work, but here we found that respiration CP easily gives us both the information in one go. So.
Okay. Yeah, you want to add on? Okay.
By the way, Kodesh we attempted, and for us it didn't work that much. Somebody, but I may check it again. But yeah.
Can the dimers be picked out using refocused inadequate or cinema D double quantum type experiments?
Sorry, what's the question? Which one?
So if you look at Q&A, that's just the one with the 14 modes, the first one.
Can't the dimers be picked by using?
It's by anonymous.
No, we tried the double quantum, single quantum. That's a good question. Actually, we tried really hard to get that double quantum, single quantum correlation. That didn't work for us, and we don't know. We tried the pulse sequence on model compounds, and there it works, but not on those samples. And I think the fast relaxation time could be one of the reasons.
How much time does it take for you to take a 1D experiment, just a normal spectrum, 1D?
CP is 40 seconds. CP is really fast. But if you take the DCP spectrum, for example, that took us 4 hours.
4 hours for one spectrum?
For one spectrum.
Wow. So it must be difficult, time consuming to optimize all these things. And
yes. It's not easy. It's not easy to optimize all those things. Sensitivity, DNP helped a lot, but still is an issue.
It's still not good enough for, to optimize the IFU and blah, blah, blah.
We can't play with all the parameters for sure.
Yep. Okay. And then next question for Oliver Lafont, what is the pore size of your sample?
Yeah, so there are the PSPP has this structure. You still see my slides, right?
Yeah, I can still see it.
So PSPP has this type of structure. So there are 2 types of surfaces. One, these wall-like surfaces here, where there can be.
So is it microporous or mesoporous?
Yeah, this we can call mesoporous, but there are also micropores sample, and I think if I remember it correctly from the paper, it was around 5.6 angstrom, the size of the pores of the micropores.
Yeah, that's quite small for the tech-pole to get in, isn't it?
I don't think tech-pole is getting in. We are using CP for that reason.
So you are probably seeing the surfaces.
We are probably seeing the surfaces, and that's what we are interested in, because phosphorus most likely.
Okay. But you can also do like a direct phosphorus, DNP, spin diffusion to look at something.
We can do that will be more quantitative for sure.
Okay.
We tried that. It does a really small enhancement, and but the point here was to look into the nature of the surface. So we need.
You're interested in the surface anyway.
The surface.
Okay. So next question from Carlos: are these pure silicon zeolites?
Yes.
If not, why did you ignore the formation of phosphorus?
These are purely, sorry, I should have been clear. Yeah, these are pure silicon zeolites.
Okay. Next question from Banu. Can you comment on the selectivity dependence on the length of short pulses for your respiration CP?
Yes. So the short pulse, basically the less the flip angle, more selectivities. And it's also, if you, for the same flip angle, if you use slower spinning, that means this long gap here, that makes it more selective. Basically, it's the chemical shift isotropy, the cross term is evolving throughout this time with its anisotropic, I think. That's what it's causing it more selective. So longer the rotor period, more selectivities. Shorter the pulses, more selectivities.
Okay. Due to time constraint, I'll probably take a few more questions. So let me just go through the questions and then Jeffrey asks, can you exploit the anisotropies in addition to the isotropic shifts?
Yes, we are trying to do that. That's why from the you mean the information, right? So we are trying to get information from the anisotropies. For example, even in same Q3 sites, the 2 Q3 sites have different anisotropies.
So that's how you identify different Q sites.
Yeah, so not only based on the isotropic, but also CSA, yes, we are using the combined information.
And then Claire Gray actually raised her hand. So Claire Gray, I've allowed your permission to speak. So yeah.
She didn't actively, she typed it by mistake, but she would be happy to talk. I was interested in why you saw the development of the CSA initially and what role temperature plays in all of this and dynamics.
So Temperature is definitely, we looked into it, and temperature does play a role. By going to higher temperature, you can reverse back actually some of the changes in the speciation. The change in CSA, because different sites have, that's our hypothesis for now, that the different type of sites have different mobility, and the environment is also changing, the symmetry is also changing. So that explains why the CSA is changed between Q2 and Q3 sites.
Yeah, and there's been a lot of calculations looking at the different CSAs of Q0, 1, 2, 3, 4, and they're very characteristic.
In the polyphosphates, that certainly there are many.
Yeah,
I don't find that many on the framework bound sites, but I would be happy to see.
A little bit on surfaces has been done.
Okay, I'll look into that.
Yeah, but thank you for the beautiful talk.
Thanks.
All right, thank you, Claire, for your question. I would just like pick one last question. So why do you choose to spin at 7 kilohertz? I think you can spin like at up to 14.
Well, that's what we could yes, that's right. At equal at 3.2 mm, you can spin up to 14 kilohertz. We couldn't, it depends on the sample packing. And in these samples, you know now that we can't just repack the sample. Once we pack the sample in the glove box, we can't open the sample or repack. So, and it depends on the nature of the sample as well. So we could not achieve more than 7 kilohertz. That's the case. We would like to go higher.
So it does not spin very stable, higher than 7?
Yeah, so the requirement for bearing and drive increases. Like with the limit that they give in the Bruker, that what should be bearing and drive, we achieve 7 kilohertz. That's the case.
Okay. All right. So thank you very much, Sheetal, for your Q&A session. So I will ask Bob to introduce our next speaker. Thank you, Sheetal.
Okay, our next speaker is IIya Kuprov, and IIya is presently at University of Southampton in the UK. And interestingly enough, he started out his career, I just learned this morning, as an organic chemist in Novosibirsk, with a lot of very famous science going on in Russia. He tells me that he almost killed himself being an organic chemist, working in an organic chemistry lab. So he decided to go do protein NMR at Oxford University, where he got his PhD. And he also says he almost killed himself there. So he's almost, had two tragic events in his scientific career. Anyway, those experiences led him very quickly to theory. And today he's going to tell us a little bit about spin, maybe a lot about spin, which is the title of the new book that he is in the process of writing. So IIya, the virtual stage is yours.
Thanks, Bob. That's an interesting story of why I'm a theorist. Yeah, I started my life as an experimentalist, but it really helps actually to know what an amplifier is. Okay, let me share my screen. And okay, can you all see it?
Yes, we can.
Lovely, let's get the presentation going. There we are. Okay, so this is a peculiar lecture in that the person I wrote it for was myself. And the reason I wrote it is that I was never entirely comfortable in 20 years of doing spin dynamics with the introductions and the explanations that were there in the undergraduate textbooks. And to my dismay, I realized that all our magnetic resonance textbooks, they simply dodged the question and started with the spin Hamiltonian. And so at some point, I looked myself up in the library and proceeded to derive the whole thing from cogito ergo sum, as you shall see, to Pauli Hamiltonian. Now, interestingly, there was one category of people who, when I talked to them, were not at all surprised about spin. Those were astronomers. And they said, well, okay, I mean, the body is rotating, so what? And to them, the quantity is unremarkable. If you have a spherical mass that's orbiting some planet, spin is simply its own rotation. And if you look at the equations of motion here, d momentum by dt is just the gravitational force and an external force that you have on the particle. And then d spin by dt is this vector cross product. In fact, in Newtonian gravity, this doesn't exist, but in general and special relativity, it does. You have a precession of the direction of spin for a macroscopic object in an orbit around a massive body. And then there's a force called Thomas force, then lens-tearing effect discovered in 1918. And if you look at it, this looks like angular momentum. And it gets crossed with spin. So this is actually the astronomical spin-orbit coupling here. And there's also a spin-spin coupling. That is the interaction between the rotation of the planet and the rotation of the body that's orbiting it due to relativistic frame dragging. And Thomas precession is a special relativity effect, and these two are general relativity effects. And they're all rather weak. You can see they all have c squared in the denominator. So astronomers are not at all surprised, and you can see the time scale of this is about right. In 1926, Uhlenbeck and Goudsmit got hold of extremely high quality hydrogen spectrum. And they saw that there were additional splittings in it that could not have been explained by Schrödinger's equation at the time. And they did what you'd expect naturally people to do. They looked around, they saw, well, okay, there's this spin-orbit coupling that looks like it fits the bill. So just times L by S, plonked a coefficient in front of it, put it all into the Hamiltonian, and it all fitted in a lovely way. And so without much ado, they published it, although they were rather bemused at the time as to, first of all, the ease with which it all just clicked in, and secondly, about what it can possibly mean. Now, this was not surprising to astronomers, but it was very surprising to physicists because, of course, this all comes from the curvature of space-time by gravitation, and electromagnetic fields do not curve space-time. And so why the thing should be a copy of that wasn't entirely clear. Another objection from Pauli was that the canonical quantization procedure implies that all the operators in the Schrödinger picture are either multiplicative or differential, and such operators cannot possibly have exactly two eigenvalues. They can either have infinitely many, or they can have none if the equation is not soluble. It is not possible for a differential or a multiplicative operator in a Hilbert space to have exactly two eigenvalues. So that was a bit of a mystery. Lorentz estimated the surface velocities that a charged particle would have to have in order to have that magnetic moment for a classical electron radius, and concluded that it would have to spin at 10 times the speed of light, which was also not terribly good news. And then, of course, exactly two eigenstates. And if you look at angular momentum, you can either have 1 for s orbital, or 3 for p orbital, or 5 for d orbital. They're odd numbers. There was no way to squeeze an even dimensional representation into the theory of angular momentum, certainly nothing that's 2 by 2. And then if you try actually squeezing it into a three-dimensional rotation group, you get a lot of bizarre things like 4-pi periodic rotation. And this is just reductio ad absurdum, right? So it was clear that something very strange was going on. And then Heisenberg read the paper, and of course, Uhlenbeck and Goudsmit simply had a coefficient to fit, so they didn't notice it. But he noticed that the classical description that they use actually is missing a factor of 2. So he wrote a letter to Goudsmit calling his paper Seine mutige Note, your brave note, and asked him quite politely what has he done with a factor of 2. Well, Goudsmit was 24 at the time. He was more or less a PhD student, and he admits quite frankly in his memoirs that he was completely overwhelmed and didn't understand a bit of it. So the paper essentially was a product of much courage, much luck, and the hydrogen spectrum that was measured by Sommerfeld. Now, of course, everybody was rather suspicious about a property that on the one hand, you essentially need, but on the other, that doesn't seem to have any good explanation for it. And Uhlenbeck in his memoirs is quite fond of this particular letter. It's from Llewellyn Thomas, a British specialist in relativity, to Goudsmit. 1926, same year as the paper was published. I don't know how well it comes on your screen, so I'll read it. I think you and Uhlenbeck have been very lucky to get your spinning electron published and talked about before Pauli heard of it. It appears that more than a year ago, Kronig, an American physicist, believed in the spinning electron and worked out something. The first person he showed it to was Pauli. Pauli ridiculed the whole thing so much that the first person also became the last, and no one else heard anything of it, which all goes to show that the infallibility of the deity does not extend to his self-styled vicar on earth, meaning Pauli, of course. And then there's a little bit of nitty-gritty here, and he writes, at present I'm still working on a longer article on the kinematics of the rotating electron. So they really believed at the time that the thing was physically spinning. And then, of course, plenty of contradictions arose. From Lorentz, he wrote to Goudsmit, that is very difficult because it causes the self-energy of the electron to be wrong. Ehrenfest, well, that's a nice idea, though it may be wrong, but you don't have a reputation yet, so you have nothing to lose. A lot of encouragement, right? Remember, Goudsmit was 24. Niels Bohr, on your way home, you should stop off at Hamburg and explain the factor of 2 to Pauli. No pressure, dude. Anyway, the factor of 2 was eventually found. Thomas found it, but everyone was intensely uncomfortable with the picture. On the one hand, it was unavoidable that you should have something like what they suggested. On the other, there was no good explanation for it. Dirac produced an interesting contribution at the time. He basically reverse engineered the relativistic energy equation. So he took this from Einstein, so E squared, M squared, C4, C squared, P squared. This is from special relativity, and said, well, why don't we just quantize it like we usually do? If this energy squared, then that's the Hamiltonian squared. If that's momentum, we must have a momentum operator in here. So essentially a bit of a hack. And then he said, okay, but we actually want the Hamiltonian itself rather than the square. And if the square depends on the square of the momentum, then let's assume that the Hamiltonian itself is linear in momentum. So he put 4 coefficients in front of the 4 terms that he had there and just squared it and demanded that he find such coefficients that make the result equal to this. It quickly turned out that such coefficients do not exist, at least when they're scalars. Dirac said, well, okay, scalars don't exist. Let's make them matrices. And it turned out that many such matrices exist. The smallest dimension that fits is 4 by 4. And Pauli matrices turned up in the blocks of those matrices that necessarily had to be here in order for this to be equal to this. Now, amazingly, the resulting equation predicted absolutely everything that was known or measured about the electron at the time, including spin. However, as Dirac himself admitted, that was a dubious hack, essentially abuse of notation. And it did predict everything, but it explained absolutely nothing. I mean, goodness knows where these Pauli matrices are coming from, why they should be there, and what on earth is this negative energy here. And that later turned out to do with the antimatter, but at the time it was much, much later. Anyway, so Dirac produced a mysterious equation that fitted everything and explained nothing. And it wasn't until Wigner published his book in 1931 that a neat derivation from the beginning to the end became available. Wigner started from basic symmetries. He used group theory to find the group invariants of those symmetries, and then he turned those invariants into the equations of motion. So what we will now do is follow Wigner's path through those basic symmetries, and eventually we will derive spin. Okay, so we will start at the very, very beginning. We will assume that reality is knowable. And that means that for any finite physical system, there must exist the possibility of describing it. That is, there must be a descriptor. Not necessarily a wave function, in fact it isn't, but a possibility of describing your finite system. We will also assume that reality has rules. That is, if system had a certain state at a particular time, that there should be an operator that takes it forward to the next time. And these are the rules. We don't know what they are, but we assume that they exist. We will also assume that time is uniform. That is, these rules do not depend on the absolute time. They only depend on the increment. That is the difference between t and t prime. We'll call it tau, so we have a u of tau. So if we had a descriptor at a time t and an evolution for a time tau, we will have a descriptor at t plus tau. And then, of course, the superposition of these operators is another such operator. They're called propagators. Information cannot be lost, so for every propagator there must be an inverse. There's a unit propagator that does nothing, and that is the list of properties required of a group. So we actually have a propagator group. Okay, the next assumption is that reality is continuous. And of course, velocities and accelerations are aspects of that reality, so they themselves must be continuous, and so every derivative must exist. As soon as it does, we can have a Taylor series. So we can take this psi t plus tau and expand it in a Taylor series using the derivatives of psi. But if we put the Taylor series into a square bracket, what you would realize that this is in fact an exponential of the differentiation operator. And so interestingly, without too many assumptions, we actually found an explicit expression for the propagator. It is an exponential of a time derivative. And in general, the exponential of a derivative is a finite shift. So this is why it shifts the things forward. This operator here is called the time evolution generator. And why don't we take a better look at it? Well, we can find its eigensystem, right? Mathematics is independent on reality being there or not. It's a logical construct. And we know perfectly well that the eigenfunction of a derivative is an exponential. And so if we were to look for a matrix representation of this operator, it would simply be a product by omega. And since it's one-dimensional, it's an irreducible representation. And then if we were to look for an arbitrary representation, we know from group theory that it's a direct sum of irreducible ones. And so in any representation of physical reality, the generator must have this form. Operators in a group representations are defined up to a similarity transform. So these are in fact in general Hermitian matrices. And so it turns out that actually the evolution equation must look like this. d by dt is minus I times some matrix. And we didn't have to make too many assumptions for this. In essence, in any knowable and continuous reality with unchanging rules, the equation of motion must have this form, and any representation of reality must evolve under the corresponding representation of the propagator group. Okay, so we have got quite far from quite a few simple assumptions. Let us now look at other symmetries of reality. Rotations. Again, rotations are a continuous group. One rotation times another is another rotation. This is called closure. There's a unit element that does nothing, and for every rotation, there is an inverse one. And it's the same game, right? So the exponential of a derivative is an increment. So exp d by d phi is just shifting f. So that must be the rotation operator. This is it. And if we go through the chain rule and express it in Cartesian coordinates, you will see the operators that we know from classical physics are angular momentum operators. So it turns out that angular momentum operators are generators of the rotation group. And you have the usual commutation relations for them. Now, the general rotation is then the exponential of the three generators. This nx, ny, nz is the vector around which we are rotating, and alpha is the angle. Now, since the content of this slide is so familiar to everybody present, you have all done angular momentum, I will use it to introduce the somewhat more general group theory. Now, notice what we have here. We have a linear combination. Once we have linear combinations, this is a space. And once we introduce commutators, the resulting object in mathematics is called an algebra. It's a space with a commutator. And then these operators, whose combinations span the algebra, are called the generators. Then this is the exponential map that gets us into the group where the rotations themselves live. And that's an element of that group, and these are the group parameters. And so rotation group is a triparametric group, three Euler angles, for example, that is generated by the angular momentum operators. And these commutation relations are called structure relations of the algebra. Now, one thing that you also know about is for angular momenta, we have an operator that commutes with everything. This is general. The algebra of every continuous group has such operators. They're called Casimir operators, and their function is in fact to commute with everything. They also enumerate irreducible representations. They are multiples of unit matrices in arrays, and they correspond to conserved quantities. So the total angular momentum is in fact conserved. And the fundamental assumption that we have made here is that reality is isotropic, right? If you rotate the coordinate system and repeat the experiment, you are guaranteed the same outcome up to that rotation. And so orbital angular momentum A exists and B is conserved just because reality is isotropic. Everything else is unavoidable mathematics. Translations. We know that we can translate things in X, Y, and Z, and also in time. And so that's the translation group where this little coefficient C has to be here to have consistent units, right? Time has a dimension of time. So this has to have a dimension of velocity for the result to have a dimension of coordinates, and everything for everything to be internally consistent. The same thing, right? A linear combination of these generators then gets exponentiated and produces a general translation. And these are the parameters of the translation group CT, X, Y, and Z. And the Casimir operator here is this in the relativistic metric. It's too far in the mathematics. I would skip the reason why these minuses are here. But let's take a look at this. The translation operator with respect to time, d by dt, remember a few slides back, it was the Hamiltonian. It was essentially energy. Right, here we have the momentum squared. And so we have a relationship here between energy and momentum. Well, the corresponding coefficient has to have something to do with mass because, well, that's the relationship between energy and momentum. And if we look hypothetically at something that doesn't have a mass, let's put this to 0. Then we have this relation and we can replace these things with their differential operators. We get this equation. This is actually wave equation. And we know exactly what this C actually means. It's the velocity of propagation for whatever this wave equation describes. So because we assume 0 mass, this is propagation velocity for massless waves. It has to be the speed of light. So you can see how elementary things come out of basic symmetries. And after you put all the correct units in here, you get the relativistic energy momentum relation, right? E squared is m squared c to the 4th plus c squared p squared. And remember what we have found out twice by now, that energy is a linear momentum in time. So the consequence of uniformity of reality is the conservation of rest mass and linear momentum, and also the requirement for there to be the speed of light. Before I move further into Lorentz group, I need to introduce a little bit of the things that chemists would not necessarily be familiar with. Michelson-Morley experiment, long before what I was talking about previously, they were trying to measure the dependence of the speed of light on the reference frame of the Earth relative to some privileged frames that they assumed had existed. And so they measured it in summer and winter when Earth was on a different sides of the sun and moving in opposite directions. And to their surprise, they discovered that the speed of light was exactly the same in all reference frames. This is the famous equipment, brickwork, turntable, and an enormous slab of concrete with an interferometer on it. So the speed of light was the same in all reference frames, which flew into the face of, for example, the Doppler effect, which was well understood at the time. So Lorentz, who had seen such things before for Maxwell's equations, suggested that the only way to reconcile, assuming you trust the outcome, it with what else is observed, is to assume that when an object is moving, it is shrunk in the direction of motion, its time is dilated. And then if you assume that transformation to be a group, that it has to obey the group properties, there's only one transformation that fits the bill, the so-called Lorentz transformation. It compresses the object in the direction of travel and also dilates time. Now, Lorentz had already seen this in Maxwell's equations, which are Lorentz invariant, but in this case, the target of the transformation wasn't some wave, it was the actual experimental apparatus, which was a bit shocking at the time. And you can see the word Versuch in Lorentz's paper, attempt at a theory of electric and optical interactions between bodies. So that was actually an early indication that matter wasn't privileged relative to waves, that you had to apply the same transformations to matter and to waves in order to have consistent physics. Okay, so Lorentz group. So this is the transformation in 2 dimensions, so time and x. In 4 dimensions, it would look very, very similar, so just such blocks for all coordinates, and this boost. Let us transform it a little bit. We will put v over c as hyperbolic tangent of this phi, it's called rapidity. Then the expression for the Lorentz boost operator is simplified, it becomes trigonometric. And then it's an exponential of this matrix. And again, you can see the exponential, a generator and a parameter. So we are now speaking, once again, group theoretical language. After you do all the chain rules, you arrive at differential expressions for Lorentz boosts, and they're actually quite similar to angular momentum expressions, except there's a plus in here. So it's not a rotation, it's a stretch and squeeze, and there's always time involved. CT, everywhere, here, here, and here. Turns out, after you work through the commutators, that boosts are not actually independent from rotations. When you commute 2 boosts, you get a rotation. So now we have in this Lorentz group, a symmetry group that accounts for special relativity, the usual rotations. You can rotate the body as per the usual, but we also have entirely new kind of rotations. You can rotate the body by giving 2 sequential Lorentz boosts in 2 different directions. So in space-time, there are 2 ways of rotating things. A rotation may also be accomplished by a superposition of boosts. Now remember how we derived rotations in the rotation group. The invariant, right, the angular momentum, the orbital angular momentum was the consequence of this commutation relation. And now we have different commutation relations, so the invariant is going to change. It is not going to be orbital angular momentum that is going to be conserved, it is going to be something else. And you can now start seeing the glimpses of the new property emerging. In Lorentz group, there are actually 2 Casimir operators, and this one, look at it. It has the total orbital angular momentum, but also the total boost. So it's not just angular momentum, it is angular momentum and something else. Now, the interesting thing here is, of course, we could have done the same as what we did for spherical harmonics. In angular momentum, solve the differential equation, get the eigenfunctions. But those of you who actually remember how it was derived would remember that the derivation was horrendous. It was actually Laplace who derived it first, and he spent like 50 pages of his book doing it. And that was 3 dimensions, and now we have 4 dimensions. So yes, you can do it, it will take 50 pages of math, but thankfully Wigner found a workaround. He said, why don't we complexify the group? Why don't we take these linear combinations of rotations and boosts and take a look at their commutations? And it turns out that the commutation relations disconnect themselves. So m's only commute between themselves and n's only commute between themselves, and they commute with each other. But this we've actually already seen, right? These are exactly the commutation relations of the rotation group, except now we have them twice. And it needn't actually be the rotation group. If you look into abstract mathematics, there are 2 groups that fit the bill with respect to the commutation relations. One is SO3, the special orthogonal group in 3 dimensions, the rotations group, and the other is SU2, the group of all unitary transformations of a 2-dimensional complex space. So this is pretty clear, and this is quite abstract. And if we are honest about it, we have to now find out which ones we have here because we don't know. We now have time that participates in our rotations. Okay, so what do we know about SO3? Well, it's 2 pi periodic. If you rotate an object around any axis by 2 pi, the operator is a unit matrix, right? The object doesn't change. And then if you rotate it by 4 pi, you still get a unit matrix, right? 2 pi periodic. This is not the case for SU2. If you do an SU2 transformation by 2 pi, you get an inversion. And then if you do it by 4 pi, then you get the identity matrix. So this group is 2 pi periodic and that group is 4 pi periodic, but in an abstract complex space. Well, let's find out what the period is of the Lorentz group. So let's take mx, for example, and take its exponential. So that's jx ikx over 2. Jx and kx commute, so you can split the exponentials up and notice this factor of 2 here, right? Ijx alpha was 2 pi periodic. Ijx alpha over 2 has to be 4 pi periodic, and the same applies to kx if you do the math. So this is in fact 4 pi periodic. And this has nothing to do with three-dimensional rotations. The reason is the presence of boosts, which introduce time as a degree of freedom. So there are 2 instances of SU2 in the Lorentz group, and we know the representations of them, so we can proceed. Okay, our Lorentz algebra complexification is a direct sum of 2 instances of SU2. And for these, we know everything mathematicians told us. So the irreducible representations, because we have 2 SU2s, we have 2 quantum numbers, and then a direct product between the corresponding matrices. If we add inversion to the group, it turns out that the boosts change sign under inversion, so that other Casimir operator, which we didn't discuss, actually gets knocked out, and only one Casimir operator remains. And then it turns out inversion also requires us to either have 2 j's equal or to have this interesting direct sum, j1, j2, direct sum j2, j1. And actually, if you look at what they physically mean, they correspond to different types of particles and fields. Fermions go one way, bosons go another way, electromagnetic fields go the third way. There are different irreducible representations of the Lorentz group. Okay, for electrons, because of Uhlenbeck and Goudsmit, we know, and also it matches Dirac's equation, there's only one irreducible representation that actually matches experimental observations, and this is this. And you can see Pauli matrices again made an appearance. They fell out of SU2. You can see a direct sum in both cases. These are unit Pauli matrices, so with 1s and -1s. But unfortunately, Lorentz group has no time translation generator. It's about rotations and it's about boosts, but it doesn't have the momentum with respect to time. And we need that thing in order to get the equation of motion. Okay, so let us go into now the giant complete symmetry group of reality, where we will put all rotations, all the boosts, all the momenta, the time translation generator, and these are all of the associated commutation relations. This group inherits the invariants from its components. It inherits the mass invariant from the translation group, where this, remember, is the second time derivative, so we can now put together an equation of motion. And it inherits this invariant from the Lorentz group, where we have the angular momentum and the boost. Okay, well, we use that irreducible representation which we have found, and we multiply these 2 invariants just term by term. So this gets multiplied by momentum squared, and that gets multiplied by 3/4, which is incidentally 1/2 times 1/2 plus 1. Okay, so we get that. We know the matrices for this, so we substitute the matrices, and we get this. And now we need to do a little bit of rearrangement, right? These are still the Pauli matrices, so this is 4 by 4. Pauli matrices have this wonderful complicated property. In practice, it means for us that sigma squared p squared is sigma dot p overall squared. So we substitute it in there. And in passing, I will just mention that this Poincaré group classifies systems by only 2 things, by mass and by something else, which we will hope eventually be spin. Okay, so after we use the Pauli matrix relation, we get here, this is minus I d by dt squared. So I will put that in and put the minus in here. And now we have what looks like a lovely equation of motion, except there's a problem. Our analysis of time translation invariants came up with a pretty hard constraint that in any causal reality, the equation of motion must have this form. It must be first order in time. But this thing is second order in time, so we have to do something. Well, actually, matrix square root is a well-defined operation. If you're looking for Hermitian square roots, this is it. That's the square root of that. You just square it and it goes in here. And we put plus or minus in here. And really the difference between plus and minus is a sentimental matter of which direction of time we call positive. We will also add electromagnetic fields. This is how momentum transforms when you add the vector potential, and the energy transforms when you add the scalar potential. With all of that in place, d by dt is this lovely matrix, and this actually is Dirac's equation, now derived properly. Now, I already mentioned that Dirac essentially guessed this equation, but ironically, the derivation that Wigner gave is only possible in hindsight. You have to know which direction to turn in all the many junctions that we have passed. I've sort of swept all the complexities under the rug, but it's only when you know the right answer that you are able to derive this. Okay, now we have a problem. Dirac had a problem until antimatter was discovered. We have these enormous negative energies in the system. All right, this is 500 kiloelectron volts. And then we have some weird coupling in here. Okay, well, let's split it up. Let's have mc squared minus mc squared, so that's the diagonal, and let's have this counter diagonal in a separate matrix. That's a sum, and that's an enormous splitting, and that's some kind of coupling between the positive and the negative subspaces, and that's our generalized momentum operator. Now, what I would like you to do now is to blink and to look at it with the eyes of an NMR spectroscopist. We've actually seen plenty of such equations. Enormous splitting and a tiny coupling. We know exactly in magnetic resonance what to do with such things. We go into the rotating frame. So interaction representation, it's called rigorously, with respect to this splitting, the frequency of this splitting, it actually has a name, it's called the Zeta-Bewegung. And its time scale is in zeptoseconds, 10 to the 20s, 10 to the minus 20 seconds, utterly irrelevant on any time scale that we care to worry about in chemistry. Okay, so that's our H0, that's our H1, a lovely, good old rotating frame approximation. So we go into the interaction representation here, and a lovely, good old average Hamiltonian series. Right, we average this out over the period of Zeta-Bewegung. To zeroth order, turns out it's a 0, but to first order, we get something. It's the sigma dot pi times the unit matrix. Now, the lovely thing you see is this was coupling the positive and negative energies, but this does not. So to first order in average Hamiltonian series, the positive and the negative energy subspaces, they stay disconnected. They evolve separately. So why don't we take a closer look at this? Okay, so I will remind you that for unit Pauli matrices, we have this relation. So we now have our average Hamiltonian sigma dot pi over 2m. Opening this up using this relation, pi dot pi, sigma dot pi cross pi. This is not a 0 because these are not vectors, these are operators. Split it up, that's our usual Schrödinger kinetic energy, and then we have something else in here. Well, let's just open up the cross. I will remind you what various things are with respect to the vector potential, scalar potential, and what momentum is. So pi cross pi is p cross p, then p cross a cross p, and then a cross a. Now that's actually 0 because these things commute with each other. That is 0 because that's just a vector. And a really boring exercise in vector calculus would convince you that that is in fact this, that is to say the magnetic field. That's quite a long story. And if we now substitute everything in, we actually have now the usual kinetic energy and the term that looks like the Stern-Gerlach term that was actually necessary for there to be a spin. And so actually, there are further corrections in here. You can go to second order in a slightly different perturbation theory, and then you get the spin-orbit coupling. Once you make this a central potential, this becomes L, so you have S dot L. That's Darwin term. It's to do with the zeta-Bewegung. Electron effectively has a finite size, and that's the relativistic mass term. Electron effectively gets heavier as it gets faster. So actually, we now arrived at the fact that Uhlenbeck-Gudsmith spin is the observable corresponding to sigma. But unlike Uhlenbeck and Gudsmith, we now know exactly where sigma is coming from. And so let's retrace our steps. We have the evidence of our own eyes that reality is causal, continuous, uniform, and isotropic. If we take causality and continuity, we get the general shape of the equation of motions, Schrödinger-like equations. If we use uniformity from translation group, we get the relationship between energy and momentum in special relativity. Michelson-Morley's experiment tells us that reality is also Lorentz invariant, and we knew it was isotropic. Once we plug that into group theory, we get the Lorentz group. We look at the invariance of the Lorentz group, we get that, and from Uhlenbeck and Gudsmith, we know that that's a half. All of this together, after a lot of boring math, gets us Dirac's equation. After we eliminate the negative energies and go perturbative with respect to the velocity relative to the speed of light, we actually get the Zeeman effect, right, to first order in perturbation theory. And if we add the scalar potential and go to second order in perturbation theory, we also get the spin-orbit coupling, relativistic mass term, Darwin term, and also something called angular magnetoelectric term. It is usually insignificant. So actually the conclusion from this is that Lorentz group has an angular momentum-like invariant, and its rest frame part corresponds to what Uhlenbeck and Gudsmith have called spin. And actually spin has nothing to do with rotations, as you can see, not directly. It makes an appearance because time is a degree of freedom in special relativity. It makes an appearance because we not just have the momenta, we also have boosts in Lorentz group. So it is essentially a four-dimensional object where time is an essential degree of freedom. And then, of course, any attempt to try and explain it in 3 dimensions is only going to lead to confusion, and you have seen all of that confusion on the internet. And so at that point, I was quite satisfied. I thought, fine, I probably now understand what is spin and where it comes from. It's a Lorentz group invariant, and it is so weird because it's not actually 3-dimensional, it's 4-dimensional space-time. And that's all I have to say. Let me see if I can get that back, stop sharing. So, questions?
All right, wow, it's a very, very interesting talk, and it's almost like, I would say, like almost like enlightening. Actually, I'm a physicist by training, and it's good to see these things like you know, it's like a renaissance to me to see all these like appearing. And also, I remember like as a physics student, I learned about all these Pauli matrices. I always wondered, how did he know all this? But it's
we've lost 50 participants. They got scared off by the mathematics.
It's also a bit late, like in Europe. Yeah. Okay. I mean, like there are some questions, but you know, this is also actually like for this session. Actually, I would encourage the participants to raise their hands to exchange ideas.
Actually, I've got quite a list here in Q&A. So yeah. Anonymous attendee says, "Will these be details be in your upcoming book?"
Yes, maybe I will. Maybe like can I allow like Len Mueller, because he raised his hand, and then like sure. Len asks his questions, then other people can type and raise your hand. Hi Len,
hey,
you yourself to talk.
Hi Ilya, can you hear me?
Yes, we can.
Great, thanks. Thanks for a wonderful presentation. So I had a question about going into the rotating frame and the approximations that are made. So it looks like a two-level system the way it's written. So the eigenvalues.
Yes, positive and negative energies, not spin, of course. Yes.
Yeah, of course. But it looks like a two-level system that you could get exact eigenvalues for and eigenvectors or
Correct.
whatever.
You can solve Dirac's equation exactly for a hydrogen atom.
Right.
Yep, solutions exist.
So my question is, often in the spin physics related to magnetic resonance, we find some interesting and unexpected properties when we consider the vestiges of strong coupling when we usually assume weak coupling. And there's some interesting physics there. I'm curious, is there anything analogous in these systems where there's some surprising and interesting physics that comes out if you don't make the approximation of going into the rotating frame, or said another way, dig into whatever the analogous Bloch-Siegert shifts might be?
Well, actually, the group that's investigating exactly this with the purpose of testing fundamental physics is Dima Butker's group in Mainz, of course. And yes, they can put considerable constraints on parameters of many candidate models by measuring with extremely high accuracy the corresponding spin properties. So yes, you are right. Dirac's equation, well, it is claimed in particular by Dirac that it is not extensible to multi-particle systems, but quantum chemists have found some serviceable approximations to that end. By the time we are talking about multi-particle systems, really, this is ill-suited. We need to go into full quantum field theory. And at that point, we are lucky if we can get a single proton calculated. This is really, really hard. So yes, you're right. Yes, it's possible, next to impossible to compute.
Great, thanks.
All right, thanks, Len, for your question. The next, I also saw Warren has a question. It's quite long.
Yeah,
Warren, would you like
it in writing? Warren, would you like me to read it?
Oh, would you like to speak, Warren?
Go ahead, but I think everybody else can read it as well.
So the matrix square root statement, I missed one word, Hermitian square root. So once you impose the requirement for the square root to be Hermitian, for a 2x2 matrix, that is sufficient constraint for the root to be unique up to a sign.
Sorry, I have a problem with that. So if I take sigma x squared, sigma y squared, sigma z squared, I get the same matrix in all of those cases.
But that's a cube. Wait a bit. Sigma x squared plus sigma y squared.
No, if I take sigma x squared or sigma y squared or sigma z squared, all of those are the same matrix, and therefore
well, only in the two-dimensional irrep of the SU2, right? If you go to, for example, 3x3 irrep or 4x4 irrep, you will find that that's not the case.
Right.
So
the Dirac equation you showed was a 2x2.
Well, but it has a momentum operator in there as well. And it's not sigma squared in there, it's sigma dot p. So in that case, I've actually tested it on Mathematica with explicit calculations. The root is unique up to a sign.
Okay, all right, thank you.
All right, so Fred Perez, would you like to speak? Your question is very long. Right, you need to unmute yourself. Yep.
No, it's okay. You can just read the question.
Let me see, where is it? Suggested a pictorial model of spin rotating flow energy. Value in such models, no. They serve only to confuse. So these three-dimensional representations attempts a three-dimensional picture of what is substantially a space-time phenomenon. It'll just get no end to confusion. And yes, there may be some obscure mathematical isomorphisms that one can find and then visualize. But there's value in not losing track of physics. Cartan particularly has muddied the water incredibly by creating abstract representations of these algebras that didn't connect directly to physics. So yes, we can find an obscure isomorphism that then looks like a fancy picture, but really it's just a bunch of invariants of a groups that we understand really well. Comprehend spin at a basic human level. Well, we have to define comprehension, right? So it's relating it to the reality around us, and our brain over the last couple of million years since the monkeys hasn't really evolved to perceive four-dimensional space-time. So the brain is unfortunately ill-adapted to perceiving these things. That having been said, I am against trying to visualize spin in 3 dimensions.
All right, Fred. I mean, I'm just curious, like, because, like, you know, for a lot of us, like, who are chemists, you know, like, so, like, all these details that you have, like, is it in your book? Is it published? And
no. Next Christmas, if I'm lucky. I mean, these things always take twice as long as you think, even if you take that into account.
Because like, all these symmetries, like, because like this is also like manifested in the Maxwell equations, where you have like the potentials and A. Maybe I was just thinking like people would be able to understand this from the classical physics if you have, because like the same kind of fairness. Okay.
No, trying to squeeze it into 3D will only confuse things. I think Art had a question.
Yep.
Just a very simple one, Ilya. That was really fantastic, by the way. But when one applies theory, you of course are hoping or expect on some physical grounds that the higher order terms aren't going to explode. How does one know that in this case?
Yeah, so in that case, this is known as regular approximation. There's a perturbation series that you have to use it. Zora, if you've ever used DFT packages, you would have come across that abbreviation. So it is the Zora approximation that gets all of these spin-orbit coupling terms and so on. And that series is convergent, assuming you are only weakly relativistic, which is okay up to about lanthanides. And the atoms that are strongly relativistic, it obviously has problems with. But then entirely different category of things turn up, in that the entire class of approximations to which Zora belongs makes the assumption that the small component, the negative energy component of the spinner is small. And in strongly relativistic limit, that's no longer the case. So the entire approximation scheme falls apart, at which point one really needs to solve the full 4-component Dirac's equation. But then extra approximations arrive to make it work for multi-body systems. And all of these approximations, they tail off at 1/c⁴. So, and actually that's the next order of accuracy. So if you go past the relativistic mass, the Darwin and the spin orbit, the next order of accuracy is 1/c⁴. And this is where a great zoo of other assumptions and approximations kicks in. So yes, technically you could continue that series, but there will be a lot of other ghosts in that machine that probably make it not worthwhile. So at that point, one has to abandon approximations and go to 4-component relativity for things like uranium core electrons, for example. And when that stops working, then we have to go into quantum field theory.
And so does this mean then, for example, scattering experiments suggest that the spin of the proton has a very large component from coupling together the spins of the gluons rather than the quarks?
Mm-hmm. Well, actually, that's a wonderful question because I have the exact answer for it. It was given to me by a specialist in a nuclear structure theory at the Euramar in Berlin. So the lady gave a wonderful talk about nuclear structure, and I thought, yeah, that's my chance to find out how exactly, the quarks are coupled inside a proton so that you get this spin and this effective interaction between them that then gives you effective magnetogyric ratio. So I cornered her in the coffee room and I said, okay, what happens inside the nucleus? Why do we have this effective magnetogyric ratio? She looked at me and said, well, have mercy, man. She said, not even the potential is currently known for the strong nuclear force. So the exact answer to your question, Art, is nobody knows.
So then we need you to give another lecture.
Well, so basically, as you know, right, for nuclei, we have an effective spin, right? It's a combination of the spin and the internal orbital angular momenta of the nucleons. And yes, nuclei can have excited states where they couple differently, and so those excited states would have different spins. But for chemistry, of course, we are always in the ground nuclear state. There's only one nucleus known where the excited state is in the ultraviolet somewhere. I don't remember what it is. Anyway, the theory of nuclear structure is in a pretty bad shape. It's not exact enough to get these quantities out. I think Christian Banks.
Yeah, great. I actually allow him to talk. Christian, you can ask your questions.
Hey, Ilya. I was wondering, in your talk, you decomposed into those irreducible representations, and you only considered one on the basis that it matches experimental results.
Mm-hmm.
I was wondering, I mean, we're 100 years further. Is there any evidence that the other irreducible representations play any role in physics?
So there's a scalar representation when both j's are 0, and that's electromagnetic waves. Right, there is a half-half representation, that's Dirac's vector, and I don't remember what it corresponds to. It's a certain class of pseudoparticles that you see in solid-state physics. Then there is 1, 0, 0, 1 representation. Those are bosons. Everything that's not a fermion. And then more exotic irreducible representations have been seen occasionally, but they are seen on these effective pseudoparticles like excitons and skyrmions. You know, on regular lattices, you can have this whole excitation pairs that do obey those group theoretical properties. So yes, you are, and in fact, the principal candidates for the dark matter, if it even exists, are some exotic irreducible representations of the fundamental symmetry groups that just don't couple to reality except gravitationally. So yes, you are right, that stuff exists, but every time I look at it, my eyes pop out. I'm not strong enough to read that stuff.
All right, yeah, thanks a lot.
Right, we have some questions. How are we doing on time, Kong?
We've already been going on for 1 hour and 40 minutes. It's actually I have to go soon. So it's up to you. Would you like to continue, and then I can make you a co-host and you can continue to host the session, or we can also call it, you know.
Let's see if there's anything interesting.
Just pick maybe one or two that you would like to answer.
There isn't really anything else that cannot be Googled up. So I say we call it.
All right. So so all the participants, all the Q&A will be booked. So this will be available, and we'll put it in a Dropbox. Feel free to comment and discuss after this Zoom webinar. So thank you very much, Ilya and Bob. Would you like to say something?
My pleasure.
Well, yes, thanks to Sheetal and to Ilya very much for 2 wonderful talks today. And we will see you next week, same time, same place. And who do you have on deck for next week, Con?
Oh, so next week we will be having Anne McDorbert and then Wing Ying Chow, a student of Hamid Oshkinat.
Yeah, so there will be sort of 2 biological talks next week to contrast with our theoretical and zeolite talks this week, all right? So different topics for solid state NMR and DNP. So thanks again to Ilya and to Sheetal. And as I said, we will see you again next week, hopefully.
All right, thank you. Bye.
Bye.